A traffic spike hits. Memory maxes out. Nodes flash red and go dark. Your production environment is down. This is exactly where the senior site reliability engineering interview begins. They will ask you to deploy a database using a standard deployment, or explain exactly what the kubelet does when a pod hits 100% CPU. Knowing how to write a YAML manifest is the baseline. Real engineering requires understanding how the cluster behaves when that state is compromised under load. Kubernetes functions through a series of independent controllers and lifecycle probes. Misconfiguring these primitives turns a localized hardware failure into a cascading outage. To map the architecture of resilience, we have to deconstruct workload identity, the routing logic of lifecycle probes, and the reality of resource exhaustion. These mechanics determine whether an administrator can build and defend a production-grade cluster. We start with workload identity. The standard deployment is the default controller designed strictly for stateless applications, like web servers or API gateways. In a deployment, a pod has no permanent identity. It receives a random alphanumeric hash as its name. If the pod dies, the replica set spins up a replacement with a completely new hash. When scaling out or recovering from failure, these pods act as ephemeral, interchangeable compute units. They pop in and out of existence without tracking historical state. This introduces the interview trap. If you attempt to run a clustered database inside a deployment, the constant regeneration and random naming will corrupt your data replication. A database cannot survive random identity swaps. For stateful persistence, Kubernetes provides the stateful set. This controller enforces a stable network identity for every pod it manages. Instead of random hashes, a stateful set assigns sequential numbers, pod 0, pod 1. They boot strictly in sequence. If pod 1 dies, it resurrects with the exact same name and attaches to the exact same storage volume. But a stable name isn't enough for data replication. A stateful set requires a headless service to function. By setting the cluster IP to none, the headless service bypasses the standard load balancer. When a secondary pod queries the primary, the service returns a list of discrete pod IP addresses, allowing direct peer-to-peer connection. Deployments exist to scale raw compute. Stateful sets exist to scale data integrity and sequential order. Beyond compute and data, a cluster requires cluster-wide infrastructure agents, such as log collectors and monitoring tools. A deployment cannot reliably enforce a one-to-one pod-to-node mapping. The scheduler might place 2 logging agents on node A and 0 on node B. To enforce a topological constraint, we use a daemon set. When the cluster expands and provisions a blank worker node, the daemon set instantly manifests exactly one pod onto that new node as it joins the network. Workload controllers dictate the topological rules of engagement for the entire cluster. Selecting the right controller is only half the architecture. You also have to manage the life cycle of the pod itself. What happens when an application is running, but entirely unresponsive to traffic? This introduces the liveness probe. Its core function is to check execution health. This diagram illustrates the logic flow. If an HTTP request or TCP socket check fails, the kubelet issues a kill signal and executes a hard restart on the container. Because it kills the container, a liveness probe is a blunt instrument. Restarting an application under heavy load only exacerbates the latency. To manage routing without destruction, you use a readiness probe. Here, the logic branches. If a readiness check fails, the container is left running. Instead, its IP address is detached from the service endpoint list. Traffic stops routing to the pod entirely, giving it time to recover. Liveness manages execution state. Readiness manages network routing state. The interview wildcard is the startup probe, a mechanism designed specifically for legacy or slow booting applications. If an application takes 2 minutes to load a cache, a standard liveness probe would kill it prematurely for failing to respond. A startup probe suspends both liveness and readiness checks, preventing an infinite restart loop while the application initializes. Probes dictate true auto-healing. Misconfiguring their distinct roles turns a minor latency event into a cascading cluster failure. The definitive systems design trap centers on the mechanical reality of pod resource limits. The scenario is direct. What specifically happens to the pod when it exhausts 100% of its CPU limit versus when it hits 100% of its memory limit? Memory is an incompressible resource. Once memory is allocated, it cannot be safely reclaimed without risking system stability. This chart tracks resource consumption against defined limits. The immediate consequence of breaching a memory limit is termination. The kubelet issues an out-of-memory error, and the pod is killed. CPU, however, is a compressible resource. When the CPU line breaches its limit, the container is not killed. The Linux kernel simply throttles the CPU time. The timeline of operations stretches horizontally. The pod stays alive, but performance degrades. Memory breaches trigger immediate restarts. CPU breaches trigger execution delays. To prevent these limit breaches, we use the Horizontal Pod Autoscaler, or HPA. The HPA continuously polls the metric server. When it detects rising utilization, it proactively scales deployments and stateful sets horizontally, provisioning new pods before the resource thresholds are hit. Note the constraint. The HPA cannot scale daemon sets. A daemon set scale is dictated exclusively by cluster topology, not application load. While resource limits exist to protect the node from the pod, the Horizontal Pod Autoscaler exists to protect the application from the user. A sudden, massive traffic spike hits the cluster ingress. The HPA detects the rising CPU via the metric server and immediately triggers a deployment scale-out, spinning up new stateless pods to absorb the compute load. Readiness probes temporarily hold the new traffic back, ensuring the fresh stateless pods are fully initialized before routing begins. Below the stateless tier, the stateful set database remains stable. It maintains data integrity and peer-to-peer communication via its headless service, despite the surrounding chaos. And on every machine, daemon sets quietly observe and log the entire event, remaining locked one-to-one on every node. This is the blueprint. A resilient architecture matches the controller to the state, separates execution from routing via probes, and scales proactively. Mastering these system mechanics separates successful senior SRE candidates from those who only understand manifest syntax. Real expertise in Kubernetes rests on a precise understanding of distributed, automated resilience.